this video, I wanted to review another use of matrices, particularly SIR models. In this first model that I will discuss, this is an SI model. Assuming that a disease could be modeled by linear systems, for a susceptible population denoted by S here, or I for the infected population denoting the individuals who have been infected by some disease. Now, in this simplified scenario, individuals must be in either one of these groups. You cannot be in either or. There is no other option. For those individuals who are susceptible, there is a probability that they may become infected. That probability is given here by A. The remaining percentage of individuals remain in the susceptible group. For individuals that have been infected, the probability of them returning to the susceptible group would be denoted by B, or else the remaining individuals remain in the infected group. We could represent this using sequences. S sub 0, I, and I sub 0 would represent your initial population in both of those groups. S sub 1 would depend on that previous day for n equals the number of days, equal to the number of days. I could represent these two sequences using a matrix equation. You'll notice that I've used the opposite probability, so an individual that remains in the susceptible group will be given by that probability 1 minus A, and the opposite value here denotes the probability of a susceptible individual becoming infected. Using the matrix multiplication, if you're familiar with matrix multiplication, reminding you that we use row by column, so 1 minus A times S sub n plus B times I sub n gives you S sub n plus 1. Once that is familiar, we'll look at a very simplified example with values. So example 1, suppose that for a population, the probability of a susceptible individual becoming infected is 5%. Of the infected individuals, 98% of those can return to the susceptible population. Now, in this example, there is no recovered group. An infected individual does not gain immunity. They can return to the susceptible group or remain as an infected individual. Because so many from the infected group, 98%, return to the susceptible group, if n is daily, so n represents the number of days, then perhaps this is a 24-hour flu bug, or perhaps this is just food poisoning, and that would explain why no one gains immunity. Something similar to that. Our probability matrix here is denoted as A, matrix A, and to give you a better idea of how that's set up, if individuals begin in the susceptible group, 95% of those remain in the susceptible group. So that is what this top left-hand corner is denoting. For individuals who become infected from the susceptible group, that's 5%. If the individuals are already infected, from a day-to-day basis, 98% will return to the susceptible group, 2% remain infected. So they have ongoing issues from the infection. Using matrix multiplication, we would take this 2 by 2 matrix representing those probabilities, noticing that each of those columns add up to 100%. And we would multiply it by the initial population in both of the groups. So here I have 100 susceptible individuals and 5 infected. By multiplying through row by column, 0.95 times 100 gives me 95. 0.98 times 5 gives me 4.9. That sum is 99.9. This represents the dot product of the vector from the first row of probabilities times that vector representing the initial populations in both of the groups. Multiplying using the second row gives me 5.1. Now, keeping in mind this is a very simplified model here, this is telling us that after 1 day, so for n equals 1, I have fewer susceptible people and more infected people. And keeping in mind, these decimals hardly make a difference for 105 people. But if this were on a larger scale, so if we had a bigger population than the sample size of 105, then that would represent a greater number of people. In example 2, here I continue only looking at the SI model, but I continue this after 120 days of transmission. Additionally, I have increased the number of individuals to 1,005. A looks the same, but I will be taking that, and each day depends on the preceding day, so I'll multiply that matrix times that vector, the initial populations, 120 times. The outcome results in the vector telling me that there are 956 susceptible individuals after 120 days, and nearly 49 if we're talking about people, we don't round, so 49 infected individuals. I've graphed that here to the right, and this again is a very simplified model, but you can see that the number of infected individuals, the highest value is 50.1, and it does level out so that it reaches that maximum quite early in this beginning scenario. You'll notice the susceptible, so these individuals that lie in the susceptible group, a large percent of the population is never infected and remains in the susceptible group. An SIR model is similar to the SI model, but now you have a recovered population. They do gain immunity. In this diagram below, susceptible individuals may remain in the susceptible group, or they may transition to the infected group. Individuals in the infected group may remain in that group from a day-to-day basis, but they might transition to the recovery group. Any individuals reaching the recovery group gain immunity, and they remain with immunity to the disease. Representing this in matrix form results in a 3x3 matrix. 99% of the individuals stay in group S. 92% of the infected individuals remain in the infected group. However, 8 may go to the recovery group. Any individuals that achieve position in the recovery group remain with immunity. For 1,000 individuals and 5 infected individuals on the initial day, we will look at this outcome after 120 days. Using that probability matrix, multiplying by it times the outcome for 120 times, using that initial population, the results here tell me that we have about 300 people that are susceptible after 120 days. 43 are infected, remaining in the infected group, and 663 are considered to be recovered. So after 120 days, you can see that population that has reached immunity, a group that has never been infected, and a group that is perhaps still hospitalized if the infection caused hospitalization. The maximum number of infections here reached 94 individuals after 28 days of exposure, so somewhere in here. That would allow us to know that if this disease were causing a need for hospitalization, then that would help hospitals know, perhaps in their area, they could approximate how many hospital beds to have available. In example 4, I want to pretend that this is perhaps about insects. So in this case, it is an SIR model, but I'm adding a group here, a group that is lost to the disease. So in this case, the disease is lethal to a group of insects. My numbers are still similar to what I had before. 99% of susceptible insects remain susceptible. For the insects that are infected, 91.5% of those will remain in the infected group. However, 0.5% will be lost. So this will be a lethal disease to those insects. 8% of those infected will become part of the recovered group and do gain immunity. In matrix form, I have a 4x4 matrix, as demonstrated here. Using that diagram, you may pause the video to get an idea for those numbers. Again, if insects are in the recovered group, if they appear in the recovered group, they remain in the recovered group, and similarly for lost insects. In the graph, as I have in this bottom right-hand corner, after 120 days, the number of lost insects reaches 39 individual insects. The number of recovered insects you see grows over time, so that on the 120th day, 58% of the population has immunity. The ideas that I have demonstrated through these slides could be calculated using any scientific calculator. If you have some programming experience, you could try modeling on your own, and you could increase these values to larger numbers than your calculator could calculate. Using CoCalc, you will see some of my calculations so that you could increase this for various populations or a different amount of days. In this diagram, I have roughly 327.2 million individuals, and my diagram is indicating 240 days of transmission. Over that time, the maximum number of insects lost to some disease was over 17 million. However, by the 240th day, 89% of the population reached immunity. I hope that this has given you an idea of how to use matrices to calculate SIR models. Keep in mind that these are very simplified models. No model that you see online or in the news is 100% correct, as they are predicting the future, and there are many unpredictable variables that are not always accounted for. I encourage you to try to come up with your own, and let me know if you have questions.